Good evening and very warm welcome to all the participants of the conference and many others to the 11th Pancharatnam lecture. Uh, these lectures were launched during the Platinum Jubilee year of the Raman Research Institute, and they're meant to be lectures, given by, illustrious people, and we are really delighted that Professor Sidney Nagel has agreed to deliver the 11th Pancharatnam lecture. And these colloquium level lectures are a part of a named series instated in honor of Professor Pancharatnam, an illustrious alumni of this institute. So I'll tell you a bit about Professor Pancharatnam. He joined Raman Research Institute as a senior scholar in 1952 and worked under the guidance of Professor C.V. Raman. He was interested in crystal optics and discovered a subtle effect in the interference of polarized light that is often referred to as Pancharatnam Berry phase in the quantum mechanics pertaining to geometric phase relevant both in quantum and classical optics literature. In fact, when his work was brought to the notice of Professor Michael Berry, he showed true scientific largesse and immediately published an article titled On the Pancharatnam Phase to draw attention to the pioneering work done 3 decades before his own. RRI has continued to work for decades on this area, and I'm really happy that this institute is kind of noticed now, quite visible in the areas of quantum science and its applications. So this Pancharatnam phase is an important area of current research with applications in topological matter too. And Professor Pancharatnam was quite versatile. I mean, later I discovered, much closer to my own field, that he also devised the earliest achromatic wave plate for his optics instruments experiments, and that was recognized and soon ported to infrared, and more recently in the area of cosmomicroground experiments. And unfortunately, Professor Pancharatnam passed away at a very tender age of 35 in Oxford in 1969. So these lectures are meant to honor his memory. And I would like to call upon my colleague, Sayantan, to introduce the speaker.
Am I audible?
Can you the slides are just going too far. All the way back. No.
One more.
Escape.
Am I audible? Oh. Okay, maybe. Okay. Maybe it is better now, or I can use another one. I think I can use that. Okay, so now it's fine at the back? Yeah. Okay, so it's a pleasure to have Sid to give this year's Pancharatnam lecture. Before going to a formal introduction, I'll give some personal account. So I had a chance to interact with him a lot as a postdoc, when I was a postdoc in a neighboring lab in the University of Chicago, and we used to share a lot of common facilities and all. So, so to me, Sid is like a magician. He looks like one with long hair, but I'm not talking about that. So, because I'll tell you why. So when I started working, I had some experience working on dense suspensions and broadly rheology and all. So then I started working with Heinrich Jäger, who is also an expert of shear-induced jamming and all. So then I was doing some experiment. Then either Joey or someone from Sid's lab, like we were discussing, so he mentioned that, okay, in these systems we find some memory effect or something. Then he gave me some paper, some PRL paper about multiple transient memories and all. So it blew my mind because I explored that dense suspension a lot. So I thought that, okay, so if you have billions of particles which are completely disordered, any arbitrary shape, how you can encode information which can be testable in the lab and you can do. So if I do, like, if you give me 1 hour, I can go to the lab, do the experiment and verify that. It was so simple. So then my first impression was, oh, I should have thought about these things. And then slowly I realized, like, actually that is speciality of SID, that it comes through deep theoretical understanding and extreme physical insight to come up with simple solutions to this, simple solutions or simple ideas that is pretty elusive actually. So time and again he demonstrated this. Another example is if you just put a droplet, like if I release a liquid drop, it will hit the surface and splash. But what Sid showed that if you do the same experiment in a vacuum, so the spreading will be smooth. There will be no splashing of the droplet. So like, I'm pretty sure it will not the first thing will come to your mind that, okay, you have to do this experiment under vacuum to suppress splashing. I mean, this is Sid for me. Anyway, so now more formal introduction. So he doesn't need any introduction in my opinion. So Sid obtained his PhD from Princeton in 1975, and next year he joined U Chicago. So where he's a Stein-Freller professor associated with 3 departments, 3 rather centers. So Department of Physics, then James Franck Institute, and Enrico Fermi Institute. So his broad research interest is broadly soft matter, but mostly disordered materials, memory formation, then instability in fluid flows, surface tension induced effects, and just to name a few. And he has received numerous fellowships and awards. Few I'll mention. So he's a member of US National Academy of Science and American Philosophical Society, fellow of American Academy of Arts and Science. So he received Oliver Berkeley Prize in 1999, Condensed Matter Physics Prize, and more recently, 2023, APS Medal for Outstanding Achievement. So without any further ado, I invite Sid to present.
Thank you. This is dead, so I'm going to have restart. We're there. Okay. Great. Well, thank you so much, Shannon. This was a wonderful introduction and great times that we shared in Chicago. Is this supposed to be on? Higher? Is this? Is this? Is this audible? No.
What about
mid? So up higher.
But I can't hear what you say.
Well, I'm not saying anything. That's why it makes a difference. Okay, so this is working? Okay, great. So it's really a great pleasure and an honor to be able to give the Pancharatnam lecture here and to recognize the wonderful achievements. And so I want to thank you so much for the invitation. What I'd like to talk about today is one aspect that's relevant to the conference that we've been having, but I'm trying to give this at a kind of more general level so that people who haven't been at the conference might also be able to understand what some of the issues are. And so this is having to do with memory in materials, memory in solids. And what I want to think about is that memory is a wonderful organizing theme for out of equilibrium matter and for the functions that matter can display. So the first thing I want to mention is, well, memories come from biology, and so much of our understanding comes from biology, but it also has a counterpart in the physical world, and that's what I want to be emphasizing this afternoon. And so the first thing is that memories are stored in different ways. And so we know this in biology, right? That is, you know that you have long-term memory, that you'll remember your parents even when you're so old you can't remember anything else, but you'll have forgotten just about everything else. But on the other hand, you are able to remember your phone number, and so it somehow must be stored in a different manner. So these things are not part of the same thing. The biology has figured out how to do this in different ways. You also have a different kind of memory that may not even be in your brain, but it's muscle memory, so that you play an instrument and you practice over and over again until that becomes second nature, or you play sports and you learn to do that very well. These are all different kinds of, is this still on? So these are different kinds of memories. You have a memory of your, not just your recent ancestors, but way, way, way back, because you've got genetic information that's stored in your DNA that has come from the millennials ago of how the genes distributed themselves in your body. Okay, so these are ways that biology does it, so it's not so surprising that physical systems should also have many different ways of storing memory. And so I'm just going to mention a few here because you're kind of familiar with them, but certainly the first memories that we had were stone and chisel. You could chip something into stone and remember it, or paper and pencil. More sophisticated, you can use a photograph or a phonograph to see or hear what you've had before. But then more sophisticated, more subtle computer memories were magnetic domains. We've heard lots in the last few years about the hot field associative memory and how that has led to the AI revolution. A special thing in glasses, which is one of my all-time favorite memories, is aging and rejuvenation in memory in glasses. And this is, again, a special thing, but it's just amazing to me that physical systems have managed to figure out how to store a memory that you wouldn't have thought was possible, wouldn't have been in there. And then there are shape memory alloys, which you may have heard of. But one thing that's particularly nice about what we've been studying recently is that you can train the material to have the memory. And one thing that you can train it to do is not just have a memory of something, but to become something different. And so you can train something to become an adaptable system, whereas most things would not be so adaptable. And so you can train things that aren't so obvious, kind of at a meta level of what you can do. So I want to give one example today, and this is the only example I'm going to be talking about of the memory. But the idea here is I'm going to tell you about what this memory is, but then I want to show you how it brings out questions and different ways of trying to approach those questions and try to answer them. So the first thing is, what is this memory that I'm talking about? Well, if you take a packing of particles, you pack them in tight, and you try to shear it, it will resist the shear, but then you bring it back to where you started again, and you shear it again, and you bring it back, and you shear it again, and you bring it back. And you want to ask, can that material learn something about what you just did to it? Okay? And so it's a slow process. You're doing this slowly. It's quasi-static. There's no time in this particularly except the time it takes just to do this as slowly as possible. And everywhere along this pathway, the system minimizes itself to be at its potential energy minimum, so the particles are always in contact. It's as simple as it could possibly be. You're just shearing this packing back and forth. And does a memory exist of this? And you should think of the complexity of this question. If you try to ask, what is the landscape for this material? It's something like the thing on the right there, that orange thing, which was stolen from one of Giulio's papers. But that doesn't even begin to give the complexity of it, because this is drawn in 2 dimensions. But really, this is in, if I have n particles and I'm in 3 dimensions, it's in 3n dimensional space. And so this is, our intuition is not set for being able to understand what happens in such high dimensions, right? So there's something really complicated going on. And the question is there a memory? And so I want to show what kind of memory you can have. And so this was 3 papers that were written almost about the same time. One was an experimental paper by Nathan Keim, Paolo Araccia, which did an experiment on this, and then a very influential paper by Sri, wherever Sri is, here, Sri is there, okay, and that's his picture, in case you didn't know him, that's him. He did a simulation of this independently, and then just a little bit later, John Royer and Paul Chaikin did the same kind of thing, but with friction. Okay? And so these are all had, the same idea behind it, but what they did was they took that packing and they sheared it back and forth. And what I want you to see here is that this is a movie of this thing, so it's being sheared down, and then it's going to be sheared up. And if you can find out where the little ball is that's moving up and down here, you'll see what the trajectory is. But what I want you to see is right about now, it's locked itself into a case where it's periodic. That is, it goes in one direction, and then it comes back to where it started, and then it follows exactly the same trajectory on the next cycle till it comes back. And after that, the next cycle is again precisely the same. As long as you drive it in the same way after it's learned a few cycles, it took a few cycles for it to figure this out, but once it's found that out, it has a memory of how it had been trained, and it's periodic from there on in. And it will be that way forever if you don't, if you keep driving it in the same way. Okay, so this is really kind of fantastic that in only 4 cycles, this very complicated system is able to figure out how to store the memory. And what you're seeing here is where it lights up is where rearrangements take place. This is not small little things where this thing is just smoothly going up and down potential wells. Each one of these things where it lights up, the whole thing has rearranged. And you can see that they rearrange, and they have to interact with each other. I mean, they're in a small enough box that you can't have these things really separated far apart. They're all talking to one another, and yet they're still able to find this periodic state. So this is a memory which I find really very surprising. And so this is an illustration from one of Sri's papers, which shows what the memory consists of. So each one of these curves is this was the very first cycle before anything happened, and this is how much the particles have moved, and you see that there's nothing interesting about that blue line. But after a few cycles, after 2 cycles, you see, well, it knows that it was sheared out to a shear of 0.06, and so it's beginning to show some signs of that. After 20 cycles, it comes right back down to 0. So it comes back to where it started after 20 cycles, right? And so that's the memory. That's showing how that took place, and it didn't happen instantaneously, but after a few cycles, it reached the final state. So how should we think about this process? How should we think about this memory? And what I want to do with the rest of this talk is present two contrasting viewpoints as to how I've tried to think about this, and they may be viewpoints that can coexist, or one might be wrong, one might be right, or there may be even other ones that can all coexist with this. But these are two, and they come from very different points of view. And that's why I want to stress that. One is to think of this in terms of local defect motion, and the other is to think of this as something, a global property of the basins in this very, very high dimensional, ND dimensional space. And so those are the two contrasting things. So I'm going to start off by talking about the local defect motion. Okay, so what is it that we mean by this? So when we think about this, this is some defect. We're going to model this as somehow a double well potential that the system could be on one side of this well or on the other side of this well. And as you put strain on the system, one side gets high with respect to the other. And instead of having two wells, one well disappears, and the system must be on the left-hand side. As you shear back in the other way, you go through a place where you have these two wells, and then when you get to this point, this is now unstable and has to flow to the right. And so this is one way of making the system change from one side to the other. But in the middle, in between these two points, it could be in one or the other state, and which state it is a memory of how the system was treated in the past, how it got there. Okay, so one thing that you should see is that after only one cycle, the system must return and become periodic ever after that. And so you can see that fairly easily. You start at one point. As long as you come back to where you started from, you trace it through either from starting below, in the middle, or wherever. And it's fairly easy just to check that that's true, that for a single object of this kind, it only takes one cycle, and you've now gotten yourself into a periodic state. Okay, so then what is the model? And so this model has been talked about by many people. It goes back to 1935, Priceoff model in terms of magnetic systems, but Mohitan, who's here someplace over there, and Shri, who already pointed out, and a number of other people. There have been a lot of models of this kind that's been put into the literature to try to explain this kind of behavior. So what is this? And so the idea here is that we just take one of those objects, which you can call them by, again, they come with different names. I'll probably be using the word hysteron because it's the elementary piece of hysteresis in the system, but you call it whatever you want. It goes by different names. And you just put down a whole bunch of these hysterons, a whole slew of them at random, and then you start the system off at some place, and you do one oscillation between one, starting off at some value, to a positive shear, then down to the negative strain, and back to where you started. And what you see is at this point, now the system, again, is completely periodic after that point. If one hysteron is already periodic, then putting them together, as long as they don't interact with each other, they're all going to be periodic, and therefore the sum of them is all going to be periodic at that point. So very quickly, this thing reaches the periodic state, and the way you look for that is that you measure the properties at where you ended up, and then you give this a sine wave, sawtooth wave going up and down, and every time you pass that your starting line in the upward direction, you just measure what the properties are with respect to this end state of the training. And so if you do that, then you get behavior that looks like the top curve here. And so this top curve starts off 0. In the middle, it looks like it's not going to remember anything, but when you get down to where it was trained at 8, it comes back down to 0 again, and then goes on its way. So it clearly has a memory of where it was trained. And then to remind you of Shreve's result, this looks very similar to what you show here, which is that after it reaches periodic state, it comes back down to 0 just at the point where the memory was supposed to be stored. Okay, so this did I went the wrong direction? Yeah, okay. So this is the memory retrieval, and this looks like, well, it's a slam dunk. This should have explained everything, except for one thing that I kept pushing on you, was that this thing was supposed to become periodic in one single cycle, and it took 10 cycles, 20 cycles in Shreve's example, for it to get to the periodic state. So it can't be quite this simple. So something else has to happen. Also, each period is, all you can get in this kind of model is it can only become periodic and repeat after every single cycle, and you see more complicated behavior than that. And so while this seems like a very, very good beginning for how to understand it, it's missing something. And so what is it missing? And so this is where the student, and the thing I just want to say is, and what really galls me about this, so why I, to be honest, why I'm not jumping up and down in favor of this model is because having worked on glasses for many, many, many years, I cannot believe that a glass is this simple. I mean, that is, it violates my inner core. And so that's not a good reason, that's not a scientific reason, but it's good enough for me. I mean, this is part of why I want to keep pressing on this. So this is what Chloe Lindemann did, and so she was a student of mine, and so what she did was she decided to, instead of taking a single independent objects of this kind, independent hysterons, she wanted to couple them together so that the behavior of this hysteron number 2 depends on which state this hysteron is, hysteron 1 is. So if the hysteron 1 is in its bottom state, let's say on the left-hand side, then the crossover point for the second hysteron is the slower value here. This is what, if one is in the minus sign, this is what you would get for where it switches over. But if this had happened to be in the plus state, then this changes, and it changes to a slightly different value. It could be higher, it could be lower, so this is the element of interaction. That is, it cares what the other state is, maybe not by much, but by something, and that's enough to start getting this thing going. So this is data from simulations to show that real systems really do have longer periods in the system. That is, in some of these systems, if you get close to what's called the jamming point, you might have to go 5 periods back and forth 5 times before you reach your initial state. So you have to go 5 times, you reach it, then another 5 times, then you reach it, et cetera. So the periodicity is 5. And what Chloe showed as well, as you increase the number of hysterons in the system, you can, putting in these interactions, these can also give rise to that same phenomenology of this. Okay, so what I want to ask at this point is one memory the only thing that you can storing here. So these are the questions you begin to explore. What is the nature of memory in this kind of a system? And so the training protocol, as I said, was you train it fully at one strain, gamma 1, this smaller one. And then what we do is we put in a larger shear. The larger shear typically is going to try to erase all of this other stuff. And we want to see whether it erases everything or whether there is still some memory left over. And this is one of the hallmarks of how you can classify one kind of memory versus another. How many things can it remember? Right? And so this, if it only remembered the blue, as long as you didn't put the red in, then this would have been in the same class as what you see in simple magnets, where you can only remember the largest strain you've put on, the largest magnetic field you've put on, but you can't, once you've gone past that value, it erases everything smaller than that. So does that work in this case? And so this is what Chloe did. So she took this, she fully trained it at this gamma 1, and then gave this strain at gamma 2, which was 8, and asked, okay, is there anything remembering? Does it remember anything about what this amplitude was? And so you look at this, and all of these things, so gamma 1 was all on this is 0, 2, 4, 6, and 8. All of these things are here, and they look like they're falling on top of each other, but not quite. You can begin to see they separate a little bit here. And there's where we want to look. And what you see in that case is that if you subtract off the 0th order case, what you see is, oh, there really is a signal that's left there. That is, you can go in here and measure how different that was from 0, and you can then tell which one of these strains, this original strain was the original training strain. And so you can do this, and so you can find this memory. And what I want to push here is that the memory, there are two memories in this system now. One is, the obvious one is, where was this peak? That's a gamma 2, which was at 8. But now, by measuring this other thing, you can also remember the stuff that looked like it had disappeared. And so this is kind of neat. This is saying, okay, this thing was trying to disappear on you, but if you're clever enough, you can go in and still recall the information that was supposedly gone. So I don't want to belabor this more. The next thing is slightly technical. It's saying, well, what does this memory remember? And what I will just say here and just state it is that, oh, the width of that peak that I was just showing you on the right-hand side, the width of that peak is set by delta, how much the interaction was. So if you can measure the second memory, then you have a new way of measuring interactions in the material, which I know no other way that you can measure the interactions between two flipping systems. And so this is a kind of a new type of thing. Okay, so this was the first way I wanted you to look at that problem. That is, looking at it in terms of the individual rearrangement events or the defects in the system and how the shear is making you move from one well to another. And this is a very local picture. But is there another way of looking at this? And this is what I want to talk about now. So once these defects have started to interact, which is what we did, well, once they were not interacting, then of course they were all local. But once they're interacting, I don't get to just lean on locality anymore. They're interacting, and so really the picture stops being simple and it gets really quite messed up in an intrinsic way. And the energy basin become connected to one another. And so this leads us into saying, well, what are the energy basins of a material like this? And so what we want to know is how do different energy basins flow into one another under some kind of perturbation? And so where do we start? And so this is where I want to go back to well, I teach all my freshman physics students coming into the classes that there's things called Fermi problems in physics, which are, he came in one day and asked his students, how many piano tuners are there in Chicago? And they looked at him and, what's this got to do with physics? But his point was that you're supposed to be able to understand what the nature of the world is. You should know how big things are. You should be able to estimate how big things are. And so I want to ask something here, a similar Fermi question, which I have no idea how to answer this, right? And that's why I'm asking you. Maybe you do, but I certainly don't. And so what I want to ask is, how many distinct ways can I pack particles in a box? And I'm going to say there are n particles in 3 dimensions, and it's a periodic boundary conditions. So that's the conditions that I'm using. And I want to know, how many ways can I do that? And how do I even think about that? And, I mean, I had 3 guesses. It's either 1, or it's 2 to the n, or it's n factorial. And then I'm stuck. I don't have any other functions that I know how to use. I mean, but I don't know which of these it is, and how do I even put it into one of these categories? And so the first thing I want to do is I want to say, well, how am I going to measure this? And the way of measuring this is something that's been around for a while, which is, well, you take your system, and you put in your particles at random, totally random numbers that you put in for all these particles, and then you relax the system and just have its steepest descent, so it goes downhill in the potential energy landscape. And so these particles are raining in from the top. This is that huge 3n dimensional landscape that I have, but only in 1 dimension, so I can show it here. And everything between here and here falls down to the bottom of this well, and that is where you've got mechanical stability at that point, and everything gets stuck there at that point. But if it had fallen over here, it would have fallen to this well or this well. And what do I mean by how big is this well is just what is this opening angle? Because that's going to tell me how many of those random conditions got me into that particular well. I don't care how deep the well is. I just want to know how many ways can I have gotten into it. And so this is a random number generator. And so this should get me to a good estimate of how big each of these wells are. OK, so now let's be specific. So I'm going to ask you, I'm going to do this, drop particles in 10 to the 7 times, and I minimize, and I get to the mechanically stable state. And if I start with n equals 13 particles, so that's a pretty small number of particles, will I find one basin even more than once? And I'm just reminding you that if you count you can put the particles in different orders, that would have been 13 factorial ways of doing it. And 13 factorial is already 6 times 10 to the 9. So even if I work very hard and get 10 to the 7 configurations, I'll never have seen the same well twice. Right? So this is bound for failure. So I'm going to try something a little bit different. And so I'm going to get rid of that thing about the rearrangements. I'm going to make them all monodisperse particles, so they're all exactly the same size and indistinguishable. Okay, so now I have n equals 13 particles, indistinguishable, and I do this, and I do it 10 to the 7 times. How many states will I find? Any takers? One? No takers for one. 10,000. You okay. You won't play this game. Okay, that's fine. So what is the answer? And so the answer was, to me, really quite surprising, is that there are only 33 different configurations that we found after this. And so that's really quite small. So instead of having this thing which was so large that I was uncountable, we've now found the situation where I can really begin to count this if I've just made this thing a little bit simpler than where I started. And so now we take these systems, and this is the probability of finding a well number n. But we've rank ordered this from the largest probability, that is the largest system, to the smallest one, number 33. And so this is rank ordered. So this has the largest number of, it's the largest well, it has the largest number of cases that we found. And down here, we found that roughly 10 times, but nothing below that. So it doesn't mean there isn't anything there, but we've covered almost all of the space. So this is what we saw in that case. Okay, so now 13 particles is rather small and clearly finite size effects, but now we want to go to a little bit bigger system. And so we go to a 67 particle system. Right? And so this is, what does this look like? And so now we do this, 10 to 7 times, and we're beginning to see that there's some reasonable structure that's coming out of this, so something that looks like there's some, I shouldn't say order, I get killed for saying order, but some kind of clarity. Good, thank you. Good word, thank you, clarity. Okay, so this is a 1 over n line. This is over 7 decades, and it's a fairly straight line on this curve. You get to judge how straight it is. It's a little bit of a bulge here, but given that this is 7 decades, not bad for a simple form for this. Okay, so the thing I want to point out is, so the question people had always asked is, well, where are the most states? And what I'm arguing is that's not the right question. The question is, where does the system have all its weight? I mean, there could be 10 quadrillion states way out here, but if they're so small and so far away and so tiny, I will never visit them. And what this has shown me is that everything that I've seen at least twice counts as I know something about what its weight is. And we've covered more than 97% of the total volume of the system. So 97% of the volume is in this behavior. And this is in where the weight of the system is. So you're really dominated by the small ends, that is the very, very large volumes. You can do this for bigger systems, and so now, as you go to larger and larger numbers, you don't get as much of the volume in here, but even for 151 particles, we've got more than 10% of the volume of the system is covered in the system. And so this is a kind of there's some structure to how these valleys, these basins exist, and why. How do you think about this structure? Okay? Where did this come from? I mean, I'm careful not to call it one distribution or another, but there's clearly some structure in here, and why? And so, I mean, my naive expectation would have been, okay, we have this, this structure, and well, it must be how you pack. I should start doing geometry on this and see how many ways could I pack this in, and why one packing should contain much more region of space than any other site. And so it must be very specific to how I pack particles in 3 dimensions. And why, would I say that? Well, if I go to 2 dimensions, we know you get something very different. And so this is this is one of the packings in 3 dimensions of 13 particles, and you can see it's all, very random. But here, with 197 particles in 2 dimensions, monodispersed, it's basically a crystal, right? These things crystallize, and there are maybe a few defects in here that are randomly placed, but this is a very different thing. It's not structure here. I mean, this is, this can't have, if it's structure, it can't have the same behavior. And so what I want to show is, well, when you look at the distribution for this 2-dimensional case, even though it is this crystalline looking thing, when you plot what the same thing, that is the distribution of volumes, you get essentially the same result. That is, it's going down roughly as this 1/n law, this Zipf's law type of behavior. So this just goes to show, I said the one way I would think about this is to try and think about how do I do geometrical packings in 3 dimensions. Obviously, that's not the right tack, because in 2 dimensions, where everything is crystal, it's somehow how the defects have rearranged themselves in here, and that is somehow a more universal, more basic thing than the packing itself. And but that's still, I don't know how to handle that problem, but still, this is why 2 dimensions versus 3 dimensions is an important question. Okay, and so then this is really what those, so this is a 10th packing, 100th, 1000th packing, and you can see that they're all basically crystalline, but with these defects, and there are certain kinds of defects that can come in here, but no matter how I count them, I'm still going to get that kind of power law behavior. Okay, and then this is looking at larger and larger systems, and you get more fluctuations, but it still basically persists. Okay, so now having said this, so I hope I've surprised you with something about what is the nature of packings in this basic thing. How do I pack particles? How many ways can I pack a set of particles? I mean, it seems like a very mathematical problem in a way, but what does it have to do with the question that I started with memories? And in the memories, what we said was, well, somehow this thing finds a periodic orbit. It goes back and forth, and finally forms into this thing which is periodic. And so what this really means is that if I have that 1/n distribution, it's equally likely, if I choose a thing at random, to fall in any decade of that distribution. So it's equally likely to fall between 0 and 10, or 10 and 100, or 1,000,000 and 10 million. I mean, it's just many states, but the volumes are smaller. And so it's basically an equal distribution on this, on the log scale. So what this is showing is, so what we did was we then took started with one packing, and we took this thing and we walked out in one direction until we fell out of that packing into a different well, and asked where did we fall up. Now we can tell exactly which ones, we have a list of all of those packings that we can say where they fell, and you can see that independent of where I started, I'm getting a pretty flat distribution. There's a little bit of a bulge in the first 10, and then after that it's pretty flat. So what that means is that if I start anywhere and I go out of that well, I fall into a new state, and I start with that and I keep going, I fall into a new state, how long does it take me to get into that top 10? Because once I'm in the top 10, then it's very likely that I'm going to repeat. That is, those are the big wells. I'm going to go back and forth between those big wells. And so you can count that, and it's a simple distribution that is falling off basically like an exponential, and only takes roughly 3 steps, 3 things before you end up in your largest, in your 10 highest wells. And those are the ones that are going to be most likely to repeat. Okay, so that's just what I wanted to kind of show you, is that this is another way of trying to explain that memory. It has nothing to do with individual defects moving. The first one was all defects, had nothing to do with the basins. This one is all basins having nothing to do with the microscopic defects. Both of them look on the surface to have some reality to them. I mean, they both seem like reasonable approaches to how to think about this, but they really come from very, very different points of view and ask very, very different kinds of questions about this and give you different answers. And so this is the power of memory, is that by asking these new kinds of questions associated with memory, you may be able to come up with new ideas as to how a solid behaves and what its nature is. And so back to the subject, so first of all, memories are surprising and non-intuitive. I hope you've seen that they provoke new questions, and you can attack them from different ways. What's wonderful about memories, especially for the conference that we're having on glasses, is that memory, in some sense, you can't have a memory if you're in equilibrium, because equilibrium means you've washed out everything in the past. And so memory, somehow, if you can find a memory that somehow essentially a tool of understanding something about non-equilibrium behavior. And it suggests these new quantities that can be measured, such as the interactions, for example. But as people in the conference know, I always have to have a bullshit line. So up till now, I hope you've believed what I had to say. I can try to defend everything I've said. Below this line, it's up to you. I mean, and so what I want to think of is that memories is a new way to classify matter. So it's not the standard ways that we do it, but it's a subject matter in its own that gives us a way of classifying things in a new direction. There are simple mechanisms involved, and they're in biology, they're in physics, and you know, you go back and forth between biology and physics, and these things can influence each other. And if you know something in physics, this will very often have a place where it will be applicable in biology. It's plural. You can make things out of this. You can actually it can be useful. It can be basically you can make them a mechanical equivalent of stem cell. So where you make the thing by introducing the memories that you want, you can make it do different kinds of functions. And for me, the thing that I really like about this is there are hidden memories all over the place. And they're far from equilibrium disordered systems all around us. I mean, the sun comes up in same time every day. My heart beats 60 times a minute or whatever it used to be. You know, and I breathe in and out at the same time. All of these are storing memories in the tissues of my body or in the landscape, right? And so if you know how to read this, you can get some information about the past. And clearly, this is what astrophysics is all about. I mean, this is their view of this. They're only up at the top, but they seem to be able to look all the way back just by being extremely clever as to how to look deeper and deeper and deeper and deeper into space and to find out what the nature of the world really is and where we all came from. And that's what memory does. And so with that, these are the people who did the work, and I thank you so much for your attention, for the invitation.
Thanks for the wonderful talk. Thanks for the wonderful talk. Any questions?
I had a naive question to begin with. I mean, so what I didn't get is defects are essential to generate memory, or because the landscape picture doesn't seem to indicate anything like that, but
That's right. So I would have said that defects certainly is one way of looking at the memory. If you can identify the defects, I mean, it's in a disordered system, identifying defects isn't quite so trivial, but the thing is that it's only one way of looking at it. That is, each defect, where you move from one side defect to the other, those are actually different basins. And so the second way I talked about it includes that too, but I didn't have to think about what was microscopically going on between those two. So I think it's somehow both ways of looking at it can be quite productive.
Right now we discuss mostly about the amorphous systems and how the memory is stored there. But if you look at another picture like our hard disks, so there also we store our data and they have the memory. So shall we relate the storage in the hard disk to the amorphous picture, or these two kind of memories are different?
So there are some memories, I mean, so that's great. So yes, there are some memories that we know very much about. I mean, and they're highly controlled, such as computer memory. I mean, and those are designed in, so specifically that we know exactly what it is that's flipping at each state. We know how to erase it. We know how to restore it. We know how to keep it persistent. And so it's not that there's engineering associated with that, but I don't think that there's a conceptual problem of how do we think about that memory. But these memories are ones that just hit us by surprise. I mean, we were walking along blindly and then this thing bit us in the leg. So what the hell was that? I mean, that was a memory that came up and we weren't expecting it. And so that's why these are particularly interesting, and it's telling us something about the matter. As a condensed matter physicist, that's what I want to know about. I want to know about the matter, and this is a way of telling me about that. Okay. So it's not that I want to engineer it. Maybe someday they could be useful, but at this point, I'm just trying to understand what it tells me about the material.
Okay, thank you.
Steve, so you introduce as key ingredients disorder, high-dimensional energy landscape, and then you drive the system out of equilibrium. If you start from a system which is already by itself out of equilibrium because there's, I don't know, no reciprocal forces, chaos, or active, this is something which is good or bad to have memories?
I love good or bad questions in physics. I mean, everything is good. So it would be different, that's for sure. That is, I have as long as I'm, let's say, this is not non-reciprocal, so I have an energy landscape. I know what I'm doing. When I do this, I can count these states, and I know something about how to treat with that. For something that has no energy landscape that it's on top of, so that you're saying it's out of equilibrium, but for other reasons, let's say non-reciprocal, whatever. Okay, I don't have these tools to use, but it's great. That means I have something new to learn. That is, if I have a memory in that system, what is the equivalent thing that I could try to do in order to pull apart how that's being stored? And how many are stored? You can ask the same question. How many memories could you store in that system? How robust are they? How can you erase them? How can you deal with them? And can you use them? So you can ask the same questions, but you do need it to be out of equilibrium. Otherwise, you've gone to bland boredom.
Thank you.
Yeah. Hi. So in the first picture, this way. So in the first way of looking at things, you talked about these hysterons, which are these steady states of this driven case, and multiple hysterons. There are some interactions between them. How do I get those in from the energy landscape picture? Do the hysterons correspond to the minima of the landscape?
Yes. So the minimum of each one of those wells is a minimum of a landscape, right? I mean, because it's there. And so given that I'm not looking at the dynamics, and I just, at each time I put a stress on, I wait till the thing has relaxed to the bottom of the well. So that is part of the energy of that whole system, and it could have been here or it could have been there, and they would have given me different energies, different minima in the second way of looking at it. It would have been in a different basin. And what I'm looking at in this case is not so much how that one part of the minimum is varying, but because these things are really interacting with one another, what's really the right picture, or a better picture for that, is how they interact with one another, and therefore they're creating a basin which has to include it and everything it's interacting with. And so that's why the second picture has more, it is more general. It is a more general way of looking at this.
So you said that if you take it out from one basin, then it is sort of equally likely to go to any of the other basins. So that is assuming...
If I kick it, I have to do it randomly. I have to kick this thing out and then it goes someplace.
So does that assume that there is no interaction between the basins?
No. That's saying that the basins are now in this 3n dimensional landscape, and I don't get to vary that. That landscape is now fixed, and what is not fixed is where I place the system in that very, very high dimensional landscape. So it's like you're, you get parachuted down into a mountainside. You don't, it's where you happen to land. Is the basin that you're in, but you're not changing the landscape by landing there.
Okay. There was a small parameter phi in the slides. What is
that was just for the people who wanted to know the details. Phi is the packing fraction for the thing. So we did this all at the same packing fraction, just so that's what was held constant.
Hello, my question is, what if there is a asymmetry in the molecule or the object you consider? It's perfectly spherical. What if it's rod-like?
Well, so look, that's quite difficult. I'm not quite sure I have a good answer for that. That is, the worst thing I could have done for myself in this picture would have been to say, oh, let's let the particles all be nice spheres, but just a little bit different in size. And then I'm suddenly faced with the n factorial rearrangements of things. You're doing something that is, if all of these ellipses are the same, at least I don't have that n factorial problem. But I do have problem of how I orient the ellipse. So instead of having 3n degrees of freedom, I'll have 3n plus 1. I'm going to screw up the arithmetic in front of you, but you have 1 extra degree of freedom for the orientation that you're going to put in. So it does make it more complicated, but it's a doable problem.
No, the reason I asked you is, in pneumatic liquid crystal, which are rod-like, and if you put it in the pneumatic state itself, the flow-induced alignment is there, which as an engineer one doesn't like. But so how would you classify that? There is a memory, even if you heat the liquid crystal to isotopic temperature, again it flows back into the same lines. The flow structure can be seen.
Yeah, so that would certainly count. That is, depending on the precise thing that you're doing to it. So if these things want to align, they will presumably find, from wherever they were, they'll find their lowest energy state. Then you could perturb it in some way, let's say shearing it, or let's just say shear it. And then it will come back and presumably into a new state because it went over some energy barrier, and so it won't be precisely the same. Maybe statistically the same, but it won't be precisely the same. And so you can play the same game here, and then if we count all of those different states, then we can ask, well, what's the different sizes of these states? And some states, so much different from others, not because of their energy being lower, just because they're so much larger. I mean, what you saw here was that I have some states that are 10 million times bigger than others, right? And you know, so there's a kind of an entropic aspect to this, which is hidden behind this, just in the size of these basins. And so we could play the same game with what you're saying. You're putting it into a more complicated view, but I don't think that that changes the nature of what I'm arguing for.
Sid?
Thank you.
You talked about muscle memory, and it sort of touched off a thought, which is that muscle memory is also a training response to repeated cyclical strain. But there, the mechanical state of the system is coupled to sort of other degrees of freedom which update the mechanical state. So have people looked at mechanical memory models of that sort, of your sort, coupled to auxiliary, other updatable degrees of freedom?
So the reason that I kind of got into this was the first model that we had, which was pre-Shri, I mean, was having a dilute suspension of particles.
Yeah, so that's the...
And that was one where we don't have a lot of the complications that come in, but
right.
it's a simpler system. And that one had so much the flavor of muscle memory.
Mm-hmm.
That is, you train it, and then after a while it loses its memory. I mean, as I know well, I mean, it's gone. And so that was already included in this physical model.
Nice.
And why is because, well, there are all these other particles around there that can kick these things and knock them out of where they were. All you have to do is put a little noise in, and this thing gets messed up. There's an element of the memory still there, but it needs to be continually trained in order to keep that memory. So in that sense, it was to me, whether it's really biological or not, I certainly would not have the hubris to go out and say that, but it certainly has some of the flavor of that, which made me think, oh, this is worth pursuing.
Okay, thanks.
Hi, Sid, here in the front. So after we do all this hard work to train this system and make it remember, how do we make it forget?
Okay, so memory is the other, forgetting is the other side of memory, right? And so different things will be different. And so if you noticed in my list of physical memories, I had pen and pencil, right? Because pencils can be erased and pens, at least I was taught, not. I mean, and that to me is a distinction between the memories. I didn't put that in cavalierly. That is, how well you can, and mechanisms for erasing are important. So in memories like the ones in this particular case, it's fairly easy to get rid of the memory because you just, so I start this thing, it was sheared back and forth here, and then say, oh, I don't like that part anymore. Now just shear it 10 times longer, and now I'm over here, and it can't remember that anymore. Or if there's temperature in the system, I just let it wait for a while, and we have to figure out how big the energy barriers are for it to go over that to enter. But that's how I would do that. But some things are surprisingly resilient. So nothing is trivial in this.
Yeah. No, yes, thank you very much. So I do like the basing picture, of course, very much. And, sort of, one way to reconcile it with the issue of the fluctuations is, the model that you've shown us, there are basins, then you say, wherever you are, you just get out, and then you find yourself a new basin, and it's sort of the total random way of doing it. And of course, if the basin numbers turn out not to grow very much, then, there's a reasonable probability that you eventually end up in the largest one. But the other way sort of, so if I'm in a basin, how I get out of the basin kind of depends, of course, on what I do. And how so there is, if I'm shearing it, there's one way of going out. If I'm doing uniaxial compression, I'm going out in another way. So it gives me sort of like a direction of where I should go. And then the sort of, the amplitude of, how far I deform it kind of also tells me how far I can go out, to explore whatever I go. And sort of part of where I go is when I go to the next basin, the difference between them is kind of like the instabilities that I've triggered, right? So there is some kind of, interplay between the deformation, the local sort of neighborhood of a basin of what you can read. And so the small numbers that you need in order to return may just be coming from, you restricted yourself to a certain way of doing things, and you're not doing it, you're not going too far, so to speak. And so the chance that you come back to where you are actually, even if there's thousands of basins, just because your focus is relatively narrow, you have a chance of coming back.
Yeah, so I mean, what look, I swept things under the rug a lot here, but this picture of it is really basically a funnel. That is, if I start with a very, very small basin, it'll never return to that small basin. But if it ever got up into the 9th basin, for example, now everything that got into 9 basins now lumped together. They will all, after that point, stay together. All those basins will behave the same after that point. And so what this is saying is we try to be agnostic and just choose randomly going out of that basin into a neighbor. But what the result of that was, it was random. That is, it was the same as having chosen at random from that. That was the point of that slide. So, but absolutely, that is, there's a lot to be learned about now. How do I strain the system? Is it too big a strain? Over what length can these things be remembered, et cetera? I mean, there's, this is just the beginning of, so the next conference on glass physics should all be about this. How about that? Good, okay.
Yeah, so I think it's related to the previous 2 questions, which was, so in all of the examples you showed, in particular the shear, the scales involved is very important, right? The periodicity scale, you didn't say very much about how that's related. Because if you have a generic landscape, and so some definition of randomness is there, right? I mean, what is a category of random landscapes that you're examining? And there's some scale of randomness there, and how does that relate to the periodicity that your system exhibits in its memory? And the other thing was also sort of the opposite of the forgetting, but there must be systems, even amorphous systems, that for whatever reason, depending on the distribution of the landscape, do not accept a memory. Is there some understanding of, something that's oddly in some complex way incommensurate with memory? Because there has to be some periodicity arising out of this disorder, but there could also be a possibility that it cannot. So I was just wondering whether you thought about it.
So let me take the second one first, because that's one I remember. Sorry. Please remind me. So it's certainly absolutely possible that some system will not remember this kind of memory. I mean, it just, and so I have no problem with saying, yep, it didn't remember. I would be surprised if there isn't some kind of memory you could put into that system, but by a different way. That is, so a memory involves the material being able to store it, but also you being able to write it in a way that impacts the material and then retrieve it. And so the retrieval is also important. And so one of the things that is not in this one, but if I had done the one with the suspension, if you train it too much, it loses all the memories. I mean, so overtraining it kills all those memories, and it cannot remember them at all anymore until you reset the whole system. And so that's one way in which I know I cannot store a memory in that region anymore once it's been overtrained. But I can store other memories, you know, and so that's how so you're absolutely right that there's memories there are materials that you can create that would not be able to store the kind of memory you want to store, but you can get the other ones. Now you're going to remind me of what.
So this had to do with just the scales of you know, the structure of your landscape, right? I mean, there's a certain probability distribution of the basins and sizes of basins. So that should, in some sense, set a scale according to which, because I couldn't see where the periodicity, the scale of periodicity, should come from some hidden scale in the problem, in your setup. So I wasn't able to see whether that can be related to the scale of, you know, some distribution that you have of the, or is it, I mean, how will I know how could I predict from it what the scale of my period will be, right? Do you understand? I mean,
I kind of get it. I mean, I would say that prediction is very hard, especially about the future.
I don't mean, I mean post-diction of how can you read it off from parameters that you might have in the problem.
Yeah, and so for systems that I know well, I can kind of, you know, so things like this, we can kind of map out of what density I should be in my system and what kind of strains I could do. But if you gave me a totally brand new system that I've never seen before, I don't think I would be able to tell you what is the best kind of memory to have. I mean, you know, because memories can be incredibly subtle as they're putting in, but very important, right? So it's not a very satisfying answer. If I know enough, I can do something, but not if you present me with something totally new.
Other questions?
Yeah, thank you for a very nice talk. Yeah.
Thank you.
Yeah, I was confused about your something about your basin size distribution. Is there a cutoff? Because you said there is 1/n, and there seems to be some problem with the normalization otherwise.
Yep, there's
right?
certainly a problem with normalization, and you know, I've been after my students to please do that 67 particle thing another 100,000, well, many more millions of times, so that I want to get that. I mean, we're at 97% of the volume. At some point, it's got to fall off the thing. I mean, it can't continue. And maybe it's curving down a little bit at the end. You have to look, but I need imaginary glasses to see that. But if we get the next 3%, then I can tell you. But you're absolutely right. It had better fall off. But there's no point fitting this with power law e to the minus 1 over n, minus n over n naught, because I don't have access to the n naught. So but that, if you ask me what do I believe, yes, I believe it has an exponential cutoff on it. But since I'm just showing the data, I didn't do the fitting.
Other questions? Okay. So I'll ask a question. So you mentioned about this training and in your first part. So I was wondering that suppose you train with a certain amplitude. So are there prediction, like if you apply like similar or other amplitude in the like perpendicular direction, can you say something?
You mean so train this one and then do this?
Then do readout in the perpendicular direction, or do a training in the other direction. So can you, so from readout, can you get any signature of that fast memory by reading out in the perpendicular direction?
So I would love to know. That is, I think that it's certainly going to be most easy to read it out, at least for these memories, I mean, in the parallel direction. In the completely perpendicular direction, I would think that would be the hardest place to do it. I do think, however, that if you trained it here and then you went to 10 degrees off, I might be able to recollect it, but don't bet on it yet. I mean, but that's the kind of, I suspect that there's kind of there's a lifetime in angle that you could do for that. But 90 degrees is a big angle. I mean,
Right.
you would think that a lot of stuff would be orthogonal by that point, but.
Yeah. Okay, so let's thank Sid for wonderful talk again. So now, I'd like to call upon our director, Professor Tarun Sauradip, to hand over a small memento.
Thank you so much.
Lecture and
Wonderful. So thank you. Thank you. Thank you so much.
also present this biography.
Oh, bravo. Thank you.
Finally, a little bit about the history of the institute and the exciting results that came out of it is Nature India RRI production.
Okay, thank you so much. Congratulations.
Nice reading.
Okay, thank you. Thank you so much. Thank you so much. I really appreciate it.
Okay, thanks everyone. So dinner has been arranged in the lawn, so please join us for the dinner. Yeah.